Thank you for attending today's virtual seminar entitled Determining Leaf Wetness with Sensors, Models, and Measurement Methods, presented by Dr. Tracy Rowlandson of the University of Guelph. Dr. Rowlandson.
Great. Well, thank you for the introduction. Today I'm going to discuss the determination of leaf wetness. So we're going to talk both about amount of leaf wetness as well as leaf wetness duration through the use of all three methods that are commonly used, which is sensors, models, and measurements. I do need to acknowledge my two co-authors, Mark Gleason, who's a plant pathologist at Iowa State University, and Brian Hornbuckle, who's the member of the Department of Agronomy, also at Iowa State University. So just to give you a brief outline of what I'll discuss in the seminar today is a definition of what is leaf wetness and discuss why we're actually concerned about leaf wetness, how we can go about determining both leaf wetness and duration. So there's three methods that I'll discuss today. One is manual measurement. We can do that for both wetness amount as well as duration. The use of sensors, which have traditionally been limited to the use of estimating leaf wetness duration, but we're looking at the possibility of using them for amount estimation as well. And modeling, where we're going to discuss both physical and empirical models and then provide some final comments as to the measurement advantages and disadvantages to each technique, as I've mentioned. So what is leaf wetness? We define leaf wetness as the presence of free water in the canopy, and it can result from predominantly three sources. One is intercepted rainfall. The other is intercepted overhead irrigation, operating much on the same mechanisms as rainfall, where we have penetration through most of the canopy. And the final one is formation of dew. I'll get into discussion as to why dew forms. And the final one is guttation. Now, from an agricultural meteorology standpoint, we ignore guttation as a source of leaf wetness. It's been shown that it's a very small proportion of the overall amount of leaf wetness on a leaf. The other issue is that we can't measure it. So it's water that is exuded from the plant itself through the leaves. It's not to say that it's not extremely important in the plant disease community, but we can't actually measure it. And so for the most part, we ignore this in terms of a source of leaf wetness. So dew forms on a surface. So in this context, we're talking about a canopy surface when it cools to the dew point of the surrounding environment. So we're talking more about the microclimate that this canopy is existing in as opposed to the overall climate of the region. And dew happens on a night where we have a clear night with calm winds. So we have a loss of long-wave radiation from the canopy itself, but we don't have a source of incoming long-wave radiation that we would typically have when we have cloud coverage. And so we promote more surface cooling or radiative cooling of the canopy itself, promoting the formation of dew. So this conversion from water vapor condensing to liquid water on the canopy. There are two processes for the formation of dew, or rather two sources of that water vapor. One is dewfall, which is the contribution of water vapor from the atmosphere. And the second is distillation. In some of the literature, you'll see this referred to as dew rise, and it's a contribution of water vapor from the soil itself. A study by Wilson et al. In 1999 looked at the contribution between dewfall and distillation on a potato canopy using simulation and measurement, and found that on conditions when we have wet soil conditions or high soil water potential, they actually indicated that 85% of the overall leaf wetness was a result of distillation, and so a smaller component came from dewfall. And I'll get into why that's a concern in some of the modeling aspects further on in the talk. So why do we care about leaf wetness? In the plant pathology community, many bacterial and fungal diseases have been shown to be related to the presence of free water in the canopy. The presence of liquid water is necessary for the germination of some spores. The temperature during this wet period is also important, as that defines or sort of dictates the rate of infection. And you'll see in some disease warning systems that have been developed based on these relationships that at really high temperatures, even if you have a long wetness period, you may have lower risk than during this optimal temperature that's defined for each pathogen. As I mentioned, leaf wetness duration is a common component of disease warning systems for integrated pest management programs, and we are seeing adoption of a lot of these programs more recently by individual growers and grower groups. From another context, the presence of dew on a canopy has been shown to cause error in soil moisture estimates for the remote sensing applications. So in recent years, we've seen a launch of the soil moisture ocean salinity satellite by the European Space Agency that measures soil moisture at the L-band wavelength. And land-based measurements of soil moisture at the same wavelength dew is shown to cause an error in those estimations. And so from that perspective, we're more interested in dew amount as opposed to dew duration. This is just a list of current disease warning systems that have been adopted. This is by no means exhaustive, but just to give you an idea that these are commonly used disease programs by growers. And the one thing that we don't want to risk is the non-adoption or the perceived element of failure of a disease warning system because we don't have accurate leaf wetness duration information. So although a lot of these disease programs are conservative, so they allow for a certain amount of error, we want to make sure that our estimates of leaf wetness duration are as accurate as possible. We define leaf wetness duration as the number of hours of continuous wetness. Now you may run into situations where you have a dew event overnight and there may be a couple of hours break before you have a precipitation event. Typically if the dry period is longer than 2 hours, then we would separate that into two different leaf wetness duration events. Anything under that, we typically consider it to be a continuous duration calculation. Traditionally, duration has been measured using leaf wetness sensors, and there's several sensors that are available on the market, and we'll get into discussion of that shortly, or through modeling, and in both physical or empirically based models. For leaf wetness amount, we describe this as the mass of water per unit leaf area, and it's expressed in kilograms per meter squared, which is equivalent to a millimeter accumulation. And traditionally, we've either been able to estimate this through manual measurements or through models, specifically using physically based models. Dew amount and duration vary significantly, or can vary significantly, in some crop canopies. For example, in the diagram for corn on the right-hand side, you'll see that the most amount of dew formation occurs at 2/3 to the top of the canopy itself. In the barley canopy shown at the bottom, we have dew formation predominantly at 2/3 to 1/2 canopy, and this changes from one crop canopy to another depending on its structure. In a canopy such as grapes, where we have wider spacing between rows, maybe not as much foliage as we do see in other crops, we don't see necessarily this difference in profile. So if you were to look at a profile using leaf wetness sensors, they're probably all going to cool at the same rate, so experience radiative cooling. Similarly, at all levels within that canopy, as well as in the morning from the evaporation side of things for leaf wetness, they're probably exposed to the same solar radiation and wind conditions, regardless of the height that the placement is at. That's not the situation in many other more densely planted canopies. And I'll show you a diagram shortly that looks at the leaf wetness duration in an apple canopy, where they showed that the duration can differ by about 6 hours per night between the top and the bottom of the canopy. So as you can see in this diagram in the lower left corner, we have a dew duration or leaf wetness duration. So I'm showing you no rain days. As I had mentioned, when we have rainfall event, we typically see penetration of that rainfall throughout the canopy, and we don't see the gradation in leaf wetness as much. In dew, we do see this situation. So in the lower left portion of the canopy, there was as little as 4 hours of leaf wetness duration, more in the 3 to 4 range. When you get into the upper portion of the canopy, we're looking closer to 9 hours of leaf wetness duration. And this becomes a question is, where do you place the sensor? What is your goal? Are you looking to estimate the maximum amount of leaf wetness duration, so the longest time period that it's present, or are you more interested in an average? And so where you place your sensor within the canopy plays a really large role in determining the amount of leaf wetness duration. So through visual and manual measurements, we can actually observe leaf wetness duration. So it requires someone to go out and look at the onset of leaf wetness in the evening, and then return again the following morning to determine what time that has dried off, and that obviously the time period between the onset and dry off is your estimation of leaf wetness duration. The problem is, how do you define when a canopy is wet? So one study looked at or defined the onset as being when 50% of the leaves were at least 10% wet. Another study said, well, we're looking at the comparison of leaf wetness sensors over a turf grass surface and indicate that the onset of leaf wetness happened as soon as droplets appeared on that turf grass surface. So when you have these two different definitions, or even possibly even further definitions, it becomes difficult to compare the leaf wetness duration depending on the technique that's been used. In terms of manual measurement of leaf wetness amount, this is very tedious and requires a lot higher level of labor. It requires going out with in early morning, if you're looking at amount, or if you're looking at the progression of dew overnight, requiring someone to sample continuously through the night as the progression of dew continues. And it's not very high tech in the sense that all it requires is that you pre-weigh paper towels. We place them in Ziploc bags. We went out and would sample. In this situation, I'm showing you an example of a soybean dew amount sample. We would swab the leaf, remove the dew on both the upper and lower surface of the leaf. In this situation, we considered the 3 leaves as one. By determining the mass change of the paper towel, so knowing the mass before plus the mass after, we can determine the amount of water that was accumulated. So we have now an estimation of the kilograms of water. And then we destructive sample and we remove this leaf and we scan it to determine its area. So we now know how many square meters that leaf was. And with the kilograms per unit square meter of leaf area, we can make a millimeter estimate of dew amount. The problem is that this is very tedious. If you want to do multiple measurements, you need several people available to do so. And it's not the most ideal conditions. I mean, no one in particular would like to go out and measure dew continuously overnight, and it requires very early morning samples. So though it may be a novel idea the first couple of times that you're out doing the sampling, that novelty wears off if you're trying to measure dew amount for an entire season. Additionally, if you're wanting to do dew duration, obviously for a disease warning system to be operational, visual observations is not feasible. And so alternatives have been looked at in terms of standardizing leaf wetness duration estimates. The other factor that we found in a study that we conducted, we were looking at 3 locations within the field, so we required a lot of manpower to do this. We wanted to see if there was variability due to soil conditions within these 3 locations in the field in terms of dew amount. What we found, however, was a great amount of leaf-to-leaf variability. So in the 5 leaves that we sampled at each location, we got drastically different dew amount estimates. So as you can see, the means, although the mean values are fairly similar, our standard deviation is nearly, if not above, half of what our mean is, indicating we just had so much variability that we could not see whether or not there were any soil influences on that dew amount at all. Obviously, if the conditions are not present for the development of dew, we don't see the variability, but when you get into high dew deposition situations, you can almost have a difference of an order of magnitude between different leaves that you're sampling. The advantages to visual and manual measurements, it's considered to be the most accurate. You're physically there, you're watching the onset of dew, you're watching it dry off, so you can get a fairly accurate estimation of the dew duration. And it's actually been used as a calibration technique for sensors, for example. So when you're first placing a sensor in the field, someone would watch the onset and make sure that the sensor also indicated that the presence of dew or leaf wetness in general happened at a similar time. The disadvantages are it's labor intensive. It's difficult to find the personnel needed to go out and do these measurements, nor do they particularly want to be out at these odd times of the day. The other problem is when we see so much variability, how many samples do you need to be representative of the field? Can you get away with only doing 3 samples in a small area? Do you need to take multiple samples over a larger spatial zone of a field? So that's the question, is we don't know how many samples we need to get an accurate estimation of dew amount. And again, are we looking for the maximum dew amount, or is a field average suitable for this situation? Now, leaf wetness sensors, so their development coincided with the development of disease warning systems, and they've certainly advanced with the use of disease warning systems by growers. They've evolved from static to mechanical sensors, and now we're into the realm of electronic sensors. An example of a static sensor would be the Duvdevany dew gauge or leaf wetness gauge. And what happens is it's a wood block that was painted red, and it would be placed out just after sunset, so it experiences the same radiative cooling as its surrounding environment. Dew would accumulate on the block, and the following morning you would go out and compare the block to a series of photographs and perhaps a calibration, and these would provide an estimate of dew amount. Static sensors were unable to provide estimates of dew duration. Mechanical sensors, on the other hand, for example, the DeWitt leaf wetness sensor, use the concept of a hemp string that would expand and contract with changes in relative humidity or the presence of leaf wetness. And this would be connected to a pen that was on a rotating chart so that you could look at the period of duration. These were not suitable particularly for dew amount. The other issue is they weren't suitable for estimating leaf wetness from precipitation or irrigation. These would only be leaf wetness estimates from dew, the presence of dew. We've since advanced to electronic sensors, and there are several commercially available sensors on the market. Some of them are resistance-based sensors, and others are more of an impedance-based sensor. But comparisons between these sensors and visual observation of leaf wetness, they've shown to be fairly accurate. But the catch to this is that if they're used properly, and very often they're not used properly or maybe not used in ideal situations. The question is, where do you place the sensor? What is your goal? What are you trying to achieve? And when you have comparison between these and you've placed sensors in different locations in the field, whether or not they're adjacent to the field and whatnot, it makes difficult for interpretation of data or data comparisons between these studies. So as I mentioned, where do you place a sensor in the canopy? What is your goal? Are you looking to determine the maximum amount of dew duration, in which case you'd place it more towards the upper portion of the canopy? If you're looking at a grape canopy, this may not be as critical a question. There's been studies that have looked at the placement of sensors nearby, so placing a sensor just outside of a field environment. As we know, if we place sensors in the sort of the management region of an agricultural field, they're prone to being destroyed, run over by equipment, whatnot. So placement to the side is sort of the ideal situation. And they've actually been shown to have fairly good comparison to sensors that have been placed at the top of the canopy, which is a positive outcome. The World Meteorological Organization provided suggested standards for meteorological equipment. Unfortunately, leaf wetness sensor is not a standard meteorological equipment, and so there's been no suggested standard. So for example, the WMO suggests that you place temperature and relative humidity sensors at 1.5 to 2 meters above the surface. No such basis has been provided for leaf wetness sensors, and ultimately, from study to study, that placement differs. Particularly the resistance sensors, so they have these interlaced fingers, are sold unpainted, and a lot of studies have been shown that these sensors should actually be painted in order to reduce the variability. So you can see from the graph on the right, we have an unpainted sensor. The circle dots are actually a sensor that's been oriented at 0 degrees, so it's a horizontally placed sensor. The squares are sensors that are placed at 30 degrees, and the triangles are sensors that have been deployed at a 45-degree angle from horizontal. And as you can see with the unpainted sensor, we have very different estimations of leaf wetness duration. However, a painted sensor has been shown to reduce the amount of variability. The issue is the treatments of that have differed. So the paint types that are used from sensor to sensor, because it's a researcher-based role to paint them, differs. The number of coats of paint that have been applied to these sensors also differs. So we've seen sensors that have received anywhere from 3 coats of paint to up to 9 coats of paint. The other issue is the treatment of once the painting has happened. So once a sensor has been painted, it actually goes through a high heat drying process in order to remove the hydrophilic components of the paint, because what we want it to do is actually to absorb the water from the droplets and disperse it. So when we have these resistance sensors, what we need water droplets to do is to bridge the gap between these wires in order to complete the circuit and have the resistance drop. And so what we do is with the paint, it actually causes that water droplet to disperse so that we make sure that that bridge is gapped and that we can detect the water on that surface. The other thing that we need to consider is the deployment angle. So we've looked at deploying sensors anywhere from 0 degrees, so perfectly horizontal, to up to about 45 degrees. And as this study shows, we see a significant difference in the leaf wetness duration, although it doesn't look like a lot, but there's a statistically significant difference between a sensor that was deployed at 0 degrees, 15 degrees, and 30 and 45 degrees, but no significant difference between sensors that were placed at 30 and 45 degrees. For the most part, researchers agree that 0 degrees is not a suitable deployment angle, just because it can actually overaccumulate rainfall, so it just ponds on the surface of that sensor. And additionally, it's not really a natural leaf angle that we would see. So for the most part, sensors have been deployed anywhere from 15 to 45 degrees, and we've shown that anywhere from 30 to 45 would probably be suitable. In the northern hemisphere, we should actually orient those sensors facing north as well. Some more recent research has looked into using leaf wetness sensors to estimate dew amount. Now, this is a study that coincided with remote sensing estimations of soil moisture. And so they were using the resistance sensors produced by Campbell Scientific and comparing that to the manual measurements that they were doing in both corn and soybean fields. As you can see, in the corn field, there's not as much variation in the dew amount samples. So these, what we see on the y-axis is actually the total leaf water, so the amount of water sampled by the canopy, normalized to a leaf area index value that was derived from an optical remote sensing platform, so using NDVI as a representation of leaf area index. On the right, we have soybeans. As you can see, there's a decrease in the R-square value from over 0.5 to now about 0.35, but you also see a large amount of scatter in terms of those manual measurements. So the thought here is, can we take sensors and calibrate it to manual measurements in order to provide us with sort of an average dew amount for remote sensing applications? The advantages of leaf wetness sensors is that they're a direct measurement. You don't require any additional measurements. You can place this in the field and be somewhat comfortable that you're going to receive accurate estimations of leaf wetness duration. The disadvantages are, and this is sort of where they get forgotten, is that you need to adjust it with crop growth. So as we showed that dew formation, the profile changes within the canopy. During high peaks of canopy growth, we do need to adjust the sensors to make sure that they're maintained. If we're deploying a sensor at 2/3 canopy height, that it stays at 2/3 canopy height throughout the season. The other thing that we need to keep in mind is they need to be cleaned. What we found is during pollination periods of corn, you could go out one morning and the sensor would almost be completely covered with yellow pollen, and so that would need to be removed. Also, there could be many other resting areas in the field, but birds will always choose your sensor, and so you actually have to go fairly frequently and remove bird excrement from the sensor surface, because what you're doing then is it's changing the threshold that you would use to determine your leaf wetness duration period. The other thing is you want to make sure that there's been no debris that has fallen on the sensor, whether it's splash up of soil during a heavy rainfall or the falling of leaves that are now covering the sensor surface rather, and then you end up with overestimation of leaf wetness duration. The other thing is, as I mentioned, birds or even other animals in the field, if you're deploying these sort of on an arm or a system where it's cantilevered away from the canopy a little bit, you want to make sure that angle is maintained, that they haven't pushed that down and you've lost your 30 to 45 degree angle deployment that you're hoping to seek. The other thing is if you're using these sensors from year to year, they do have a certain lifespan, and what you want to make sure is that they're still operating from one season to the next. So it's ideal that you calibrate these sensors before you place them in the field, and this can be just as simple as putting an array of sensors in the same environment, so over a turf grass region, for example, where they're exposed to the same meteorological conditions, and make sure that the sensors are behaving similarly to one another. And if you see one sensor that is erroneous compared to the other, you can remove that and not risk failed estimation within the field itself. Now, getting into modeling of leaf wetness sensors, there's been a lot of research that's looked into using models to estimate both duration and amount, and they've actually been successful in doing this. And the comparison for these models' success has been based predominantly on leaf wetness sensors. So these models describe the interaction between the surface and the atmosphere. So the surface in this scenario would be the crop canopy, and in some models, some of the more complex models, we actually take into consideration what's happening in the soil itself. Most of the physical-based models are based on an estimate of latent heat transfer. So what we have is a positive latent heat flux at night, so positive exchange of energy to the surface, indicating the onset of dew. And then we use the negative heat flux during the day to estimate how much time it's going to take to evaporate off the leaf wetness that we have. Some of these models can also be used for rainfall if we know approximately how much rainfall a canopy will accumulate on a leaf, and then also evaporate that water off using the latent heat flux from that as well. The one benefit of physical models is they can be used anywhere in the world. The physics don't change. However, with empirical models, they're really only valid for the region in which they've been developed. So if I develop a model at the University of Guelph, it may not be applicable to use somewhere in the southern United States. And these actually require localized calibration in order to be successful. Physical models tend to be more complex and have more inputs. And so, for example, these are some of the typical meteorological inputs that are required. We have air temperature, wind speed, precipitation, vapor pressure, which we can typically garner from relative humidity, atmospheric pressure, as well as incoming shortwave and longwave radiation. Now, from an operational disease warning system, this can be a setback, because if you're not operating this weather station yourself, there could be a delay in the transfer of this information. And when you're required to produce a disease risk estimate on a daily basis, physical models may not, you may not get the information fast enough in order to use a physical model for these estimations. So there's a limitation there. Additionally, incoming shortwave is measured more often than incoming long-wave radiation at weather stations. Neither of these really are a common measurement that happens at all weather stations. So the availability of this data in the first place may become limited as well. The benefit of physical models is they're actually able to provide us with both due amount and due duration. The models are either what we call a one-source model, and they take into consideration only the dewfall contribution. So remember, we have these two sources of water vapor, so one from the atmosphere and one from the soil surface. Or it can be a two-source model, so in which case we're looking at the contribution of both dewfall and distillation. The problem with only one-source models is we may significantly underestimate the amount of dew present and ultimately underestimate the leaf wetness duration, because we haven't taken into account that water vapor source. And when we're using these models, typically we're using above canopy sensors or canopy meteorological variables that are taken off out of the field site, so we're not measuring the microclimate itself. So we may not be capturing what's necessary to accurately measure dew amount or dew duration. What these typically do is consider the canopy to a big leaf. So we're monitoring the energy balance of a single leaf and considering that to be representative of the entire canopy. Some models get a little more sophisticated, and they actually separate that canopy into different layers and look at what's happening between those individual layers in the canopy. However, for the most part, they're assuming that this layer is representative of an entire field or the region in which you're looking. Empirical models, however, typically require fewer inputs, but as I mentioned, they're really only applicable for the region in which they're developed and do require localized calibration. One of the more commonly used empirical models, certainly the one that requires the fewest inputs, is looking merely at a relative humidity greater than or equal to 90%. So what this model is saying is that if your relative humidity measurement is equal to or greater than 90%, we have dew present or leaf wetness present. And as soon as it drops below that threshold, we indicate that it has dried off. Now, some of you might say, well, really dew should only form when we're at saturation, so relative humidity of 100%. But we're not taking into account in this situation, or what it's doing is using a relative humidity measurement that's not actually within the microclimate of the canopy, and hence that threshold is even lower. A study looked at whether or not this threshold was appropriate for different regions around the world. So it examined a location in Ames, Iowa, so a research station at Iowa State University. Looked at a site in Elora, Canada. So Elora is the base for a lot of the field research that happens at the University of Guelph. A site in Florence, Italy, and a site in Brazil, and looked at what the appropriate threshold was at these different locations to determine whether or not it could estimate leaf wetness duration. As you can see on the x-axis, there is measured leaf wetness duration in hours. So this was provided by a leaf wetness sensor that was deployed in these canopies, versus on the y-axis, the estimated leaf wetness duration provided by this relative humidity threshold. And it was found for the site in Brazil that 90% was an appropriate threshold. It did a fairly good job of estimating leaf wetness duration. A slightly higher threshold had to be used for Italy, and a threshold as low as 83% was determined to be most appropriate for the site in Ames, Iowa. So this is showing how different these thresholds can be from one location to the other. If you're using the 90% threshold in Ames, Iowa, you would significantly underestimate the dew present for an Iowa site. Beyond just a localized calibration, what we also need to do is look at the sensitivity of the sensors themselves. So relative humidity sensors are not perfect either. Most sensors have a plus or minus 3% accuracy. We get into even the most commonly used sensors at meteorological stations. We see a decrease or a loss of accuracy once we hit relative humidity greater than 90%. So the accuracy goes from plus or minus 2% to that 3% that's more standard with other relative humidity sensors. So when we use the relative humidity threshold of greater than 90%, we don't see as much variability between those sensors in terms of the number of days they estimate until the next threshold is reached for a disease warning system. However, with a relative humidity threshold greater than 90%, as you can see, we can have almost 15-day difference between the sensors. So not only do we need to calibrate these disease warning systems for the location that we're at, but we actually have to take into consideration the sensor that we're using. The advantages to modeling leaf wetness duration is it can be used when we can't do a direct measurement, whether we don't have access to a field, we don't have the personnel available to go in and do manual measurements. This is a great alternative. Additionally, if you're using meteorological data from a Met service station, the calibration of this data becomes the responsibility of that service. It's not on the onus of the researcher to make sure that these sensors are working optimally. The disadvantages are they can require a lot of inputs. So as we mentioned, not all of them are even measured at most Met stations. So this would be certainly a drawback. Additionally, data may not be available on a fast enough basis in order to have an operational disease warning system. The other thing that we need to keep in consideration is the quality of data that we put into these models. If we don't have good quality data going into the models, we're certainly not going to get a good quality response. So it's this mantra of garbage in equals garbage out. So we need to make sure that we have the most accurate information going into these models in order to be confident and comfortable with the leaf wetness duration or even the dew amount estimates that are coming out. Just a few final comments. So manual measurements are probably still the most accurate and will probably be the basis for calibration even into the future. However, they are very labor intensive. And beyond sort of doing this every once in a while calibration check, not an ideal scenario for estimation of duration or amount. Sensors are accurate for duration and they show potential that we could use them in the future with calibration to estimate dew amount. They're direct measurement, so we don't have to have any additional inputs required for them. The one thing that we need to be careful of is where we put them and how we orient them, and to make sure that information is available. So taking care as to where within the crop canopy we place them, having some knowledge of the profile of leaf wetness within the canopy in order to guide us with placing them accurately. But to keep in mind, the important thing to keep in mind is that they do require maintenance and some calibration. So this is not just a set it and forget it type of situation. It will perform accurately as long as we've taken the steps needed to make sure that we have good estimation coming from the use of sensors. Models can provide both the amount, an idea of the amount and duration of leaf wetness, and depending on the model, obviously with empirically based models, we're not going to be accurate with estimation of dew amount. They don't require any direct measurement, so this can be done using data from a Met service, or if you have a weather station deployed in a field site, we can make estimates of duration. But depending on the model that you're using, it can require many inputs, and the equipment that you're using for the model, if it's under your responsibility, does require its own calibration. And some of these are sensors that we would be required to send back to the factory in order to have the calibration done correctly. The problem right now is that there's a lack of standardization for both sensor and model usage. As I mentioned, the World Meteorological Organization has suggested standards for meteorological measurements. They don't have a suggested standard for the placement of leaf wetness sensors or the use of them. And so you can see in the literature that these have been used in a variety of environments and a variety of sensors have been used. So for example, the resistance sensors that are sold unpainted require some sort of painting, but even the amount of paint or number of coatings of paint rather that have been used for the sensor differs from researcher to researcher. There is a sensor on the model market by Decagon that doesn't actually require painting. It's looking at the comparing the dielectric of air, which is 1, to the dielectric of water, which is 80. So if there's water present anywhere on that sensor, it will detect it, which is a bonus compared to some of the traditionally available resistance sensors. Additionally, there's been no suggested model that's been used, either whether it's physically based or empirically based model. There's no standard that's been used for the estimation of dew duration. But ultimately, however you choose to go about estimating leaf wetness duration, I encourage you to know the limitations of the procedure that you've chosen to use in determining leaf wetness duration and or amount, and whether or not we can actually do both of these with the technique that you're using, and have some idea of what your goal is, whether or not you're looking at defining the maximum leaf wetness duration, or if an average is suitable for a canopy. The same goes for dew amount. We don't have time to take your questions today, but I encourage you to submit your questions, and I will respond to your questions via email in the near future. Thank you.